Today we'll explore training decision trees. Decision trees are an approach to regression or classification which is conceptually simpler than many of the models we've studied already. It's the sort of thing you can execute by hand with no computational assistance because it's just based on a flowchart. So we'll come up with a few different visualizations for that flowchart, starting with indented code in the form of if-else statements. Let's suppose we have the following pseudocode, which we're told determines the color of a given flower based on its petal width and length. So we check if the petal has width less than 4, and if so, then we go into this sequence of branching statements, and if not, we're able to conclude that the flower is red. In the first case, if the width is less than 4, then we check whether the length is less than 1, and if so, we can determine that the color is blue, and if not, we proceed with checking these conditions. So part A asks us to draw a 2D region that shows the classification plot corresponding to this piece of pseudocode. So if the width is greater than 4, we know the flower is red. Within the remaining region, if the length is less than 1, we know the flower is blue. Among the remaining points, if the width is less than 2, the flower is green. And finally, in this remaining rectangle, it's green above 3 and blue below. In part B, we're asked to draw the same decision tree, but in the form of a flowchart. We call these nodes at the end leaf nodes, and the other nodes we call decision nodes. And notice that we've standardized things a bit by ensuring that every decision node involves checking one of the features, either width or length, and specifically checking whether it's less than a given threshold. That way we can spare a bit of notation by always sending the observations which satisfy the condition to the left and the ones that don't to the right. This last question asks us whether we could have done it with any fewer decisions. And the answer is no, because each decision only introduces one vertical or horizontal line. And here we have 4. So there are multiple possibilities to how we could get there. For example, we could make this cut first, then this cut, and finally this one. Or we could make this cut, then this one, then this one, than this one. However, 4 is the fewest number of decisions we could use to make this particular classification plot. Another piece of vocabulary to introduce is the depth of the tree, which is the length of the longest directed path in the flowchart. So here, it would be 4. Limiting the depth is one of the most basic ways to manage the computational complexity of the decision tree as well as mitigate overfitting. So there are many possible ways you could proceed in choosing the features and the thresholds for each node. It turns out that it's infeasible to do this in an optimal way. So to get around that, we're not going to look ahead. We're just going to make the best cut that we can at every step. And the way we're going to measure the best cut is going to involve a quantity called the Gini impurity. And this is a very natural quantity to describe how diverse a labeled set of objects is. The idea is that we want to define the Gini purity to be the probability if we draw 2 elements at random from the set with replacement that we get the same label. In this picture, that we get the same color. So for example, the probability that we get green twice is 3/7 squared. The probability that we get red twice is 2/7 squared. And the probability that we get blue twice is 2/7 squared. So this is the Gini purity, and the Gini impurity is just going to be 1 minus that. So that's the probability if we select 2 elements at random with replacement that we get distinct labels. So that's the Gini impurity for a particular collection of labeled objects. And when we choose a threshold along which to split our training set, we're going to get 2 Gini impurities. We're going to get one corresponding to all the points that go to the left node and another corresponding to all the points that go to the right node. So to combine these 2 Gini scores, we'll multiply them by the proportions of the points that go to each node. So this is a weighted average of the 2 Gini scores, with the weights coming from the 2 proportions of the split. This provides some incentive to have more even splits. That's desirable because a node that handles only a very small number of training points is unlikely to be particularly useful in the final model. So let's take a look at this visualization. It shows us for a variety of different possible thresholds along the first feature, so we're only looking at vertical decision thresholds here. When we're at the extreme left, the proportion of points to the left is very small, and the Gini impurity to the left is very low, but we end up with a high overall loss because most of the points are to the right. So this green curve is showing the total loss. The blue curve is showing the proportion contributed from the side on the right, and the red shows the proportion contributed from the side on the left. And as we move the slider to the right, the situation gets strictly better for a while because we're making a more even split, and the Gini impurity to the left remains equal to 0. But then as we continue to make a more even split, we actually see an increase in the loss because now both sides have a fairly high Gini. And then it's the same situation playing out on the opposite side by symmetry. So if we decided to split along this feature for this problem, which we would because all of the horizontal decision boundaries would lead to worse results, we'd end up selecting this point because it has the lowest loss. So in problem 2, we have a game where we run this function called Gini game, and it takes as an argument a number, and it selects the number of red balls uniformly at random between 1 and that number, and the number of blue balls uniformly at random between 1 and that number. And along each row, we have a different split. And sometimes it's very difficult to guess which is going to have the better loss. Like in this case, it hasn't done a good job of producing a low Gini impurity in either box, whereas this one has a very low Gini impurity of 0. However, it's done a very poor job of coming up with an even split. So we can run this line of code, which works because Gini game is defined to assign a value to this global random variable score report. And we find that in fact they're very close. The second one ends up being slightly better, but it probably would have been impossible to tell that by eyeballing it. Here we have an instance where we can tell, because the division is a little more equitable for the bottom row and it achieves 0 Gini impurity. So the bottom row is substantially better. Here again, it's probably quite hard to tell, and indeed they come out close, but the bottom one is a little bit better. So the purpose of this game is just to help build some intuition for what the Gini impurity is telling you and what the loss function gives. So let's move on to problem 3, where we're going to generate some data that conform perfectly to a particular decision tree, and we're going to see if we can train a decision tree to recover these decision boundaries that we started with from the data. The easiest way to sample uniformly a point in the green region is just to sample uniformly a point in the whole square and check whether it falls in this region. If it doesn't, we'll throw it away and sample a fresh point uniformly at random from the square and check again if it falls in this region. And we repeat this process until we get a point that is actually in this region. And with high probability, we'll find such a point in a relatively modest number of turns, and indeed the point will be uniformly distributed in the green region. So we'll begin by defining functions which check, is a point x comma y in the red region, is it in the green region, is it in the blue region? Now we want to define functions which will sample points from each of these regions. And what we'll do is parameterize that function by this checker function. So we can just plug in is red or is green or is blue and get a point of the corresponding color. We'll call it rand point, and it will take as an argument is color, which is going to be one of these 3 functions. So the idea is that we first sample a point from the bigger square, the 5 by 5 square. And if it's appropriate, then we return that value. If it's not, though, the way we've written this function, it won't return anything. So what we need to do is apply this whole process repeatedly until we actually do return a value. The easiest way to do that is just make a forever loop, which in Julia we can do by saying while true, and then it's going to perform this operation repeatedly until eventually this return statement is hit. So now let's make a scatter plot, and we'll do that by defining a function because we're going to need to repeat it later. So we'll begin by defining a plot with just some parameters and no contents. And what we want to do is for each color, generate some points and scatter them. So this didn't work, and the reason is that rand point returns a vector, and plots.jl wants to receive a tuple. If you're going to give a single list that's supposed to contain x and y's in pairs, those pairs should be tuples, or else plots has a different interpretation for them. So this is what we get, and this looks very reasonable. So next we want to train a decision tree classifier on these data and see whether it recovers the boundaries. To do that, we need to take our points and form them into a feature matrix, where rows correspond to observations and columns correspond to features. So initially, we have an array of arrays. we need this to be a two-dimensional array rather than a one-dimensional array of one-dimensional arrays. So the first thing to do is transpose each of these arrays to get a row vector, and then we'll just want to concatenate the resulting 100 vectors vertically. So that's vcat, but this won't work because vcat doesn't take a list as an argument. It takes the things it's supposed to concatenate directly as arguments. So we have to splat this list out into this vcat operator, and that gives us what we're looking for. So that's for blue, but we want to make 3 of those. So we get a list like this, and that's going to be 3 two-dimensional arrays, and we'll want to vertically concatenate those to get a 300 by 2 array. So this is another vcat operation. And that's perfect. For our labels, we generated these so that class 1, class 2, and class 3 appear in blocks, the first third, second third, and last third. So what we can do is just repeat 1, 2, 3 like that. So it didn't do a perfect job. It didn't clip off this left edge of the blue rectangle. But actually that's because our depth wasn't big enough. If we switch to a max depth of 4, then it'll do a very nice job of recovering the boundaries. So this was an ideal scenario for a decision tree, and it did handle it well. However, it is possible that the decision tree training process wouldn't find the correct decision tree, even though the data were generated perfectly according to a decision tree. And that's because it's using a greedy process to try to find the right fit, and not some sort of exhaustive search or guaranteed algorithm that would necessarily find the correct model if one exists. So decision trees provide a very nice context for thinking about a beautiful idea from computer science called recursion. The key point is that we can avoid having to think about coming up with a system for managing the overall shape of the graph by just representing the relationships between nodes locally. So for example, this first node will have some information about which feature it's selecting on, the threshold it's using to select, as well as the 2 nodes that it distributes decisions to. Likewise, this node will keep track of its feature and threshold together with its left child and right child. These nodes are different. These are leaf nodes, so they really only need to keep track of the prediction that they return. And the point is that if we just know the root node, the starting node, as well as these local connections, then that implies the overall structure of the tree, and we don't have to keep track of it separately. So data structure-wise, we need 2 things. We need a leaf node, and we need a decision node. And these are both special cases of a node, so we'll also want a supertype of these 2 types, just called node. And the reason it's important to have this extra type is that when we store the left child and right child, we want to be able to say that both of those are nodes, but we won't know from the outset whether they're leaf nodes or decision nodes. So let's fill in our fields for the structs. The leaf node, as we said, just contains a prediction. And the decision node contains a feature, which will be an integer. That's an index indicating which column of the feature matrix this decision node is acting on. A threshold to split left and right. And then 2 nodes. So we'll call this supertype abstract node, following the Julia convention to include the word abstract, that this represents a supertype of concrete types rather than a concrete type itself. And we're already using abstract node here by annotating left child and right child, these 2 fields of decision node. So we have some templates here to fill out with doc strings. First, we're supposed to return a vector of class counts for the points whose feature value is less than the given threshold in that particular column, or greater than, depending on op. We'll be able to put in a less than sign or a greater than sign. So we'll begin by coming up with a list of all of the actual labels. And Y is going to contain repetitions, so we want to get rid of those repetitions for purposes of knowing what the actual labels are. Next, we need a way to keep track of the counts, and we can do that with the dictionary. So the keys of the dictionary will be the unique labels, and initially the values will just be 0. And they're counting, so we want to make them integers. And if we want to make a dictionary out of 2 lists, we should zip the lists first. So next, we'll just loop over our data set and increment the counts according to each label that we see. So we check the threshold condition, except that we don't know whether it's going to be less than or greater than. We need to make this general. So instead of the usual infix notation, we'll use the standard function notation, op of 1 argument, comma, the second argument. So as a side point, in Julia, operators are functions just like any other, and they can be called in the traditional way, as well as the infix notation. And it says we're supposed to return a vector of class counts. So we need to extract the values of this dictionary, which returns a value iterator, and then we need to collect it to get an actual vector. So that function is just performing the counting. We need to use those counts to come up with Gini impurities and use that information to decide how we should split the data. And we're going to break that problem down too by first focusing on a particular feature, let's say feature I. So let's define the Gini impurity of a vector of proportions p. So we decided that's 1 minus what you get when you square each entry of p, so that's p element y squared, and then total up the results. Next, we'll define a loss function, which is what we're going to try to minimize. So we'll get our counts to the left using the function we've already written. And then the total number of points to the left is just going to be the sum of that vector. And then we'll do the same idea for the points to the right. Finally, we return the loss value. And notice we're using the total rather than the proportions here because the two are the same up to division by the total number of points. And so we can minimize either one. So next we want to find which threshold actually gives the optimum split. And here there's a little bit subtle numerical computing point to make. If we think about what happens in a generic situation, if we wiggle the threshold a little bit to the left and to the right, it typically won't hit any of these points. And so the loss will be exactly the same throughout that neighborhood. In other words, the loss function is actually piecewise constant. Between any consecutive pair of points, as ordered based on the value of the feature that we're splitting along, the loss function is the same. And this actually makes our job easier from an optimization point of view. We certainly can't use gradient-based methods because the gradient would be 0 pretty much anywhere we start, either 0 or undefined. However, because we know that the function's value is constant throughout all these intervals, we can just check the midpoints of the intervals. So we define a function called midpoints, which takes a vector v of values and first of all sorts them and then comes up with the averages of consecutive points. And one easy way to do that is remove the last element, remove the first element, add the two arrays, and divide by 2. So the x's we're going to check are the midpoints of the vector we get when we slice the feature matrix along the column of interest. So this is the ith column that we're focused on for the moment. So what we'll do is calculate the loss, and then we'll use the findMin function, which loops through the whole array and finds the smallest value as well as the index corresponding to that value. Then whichever index that is, we need to pull out the corresponding element of x, because that's where the minimum occurred. That's where our threshold is going to be. And then we'll return the minimum value and that threshold. Finally, we can define a split data function which doesn't take a feature index and does its own reasoning about which index to use. So we split the data along each column and form an array. And once again, we use the findMin function to pick the smallest one. So we pull out that pair from the feature mins vector and then look at the second element. That's going to be the threshold because we returned that as the second entry here. And then we just return those values, the feature index to split on and the threshold, because that's the information we're going to need to actually assign to a node during the training process. Which feature do you split on and at which value do you split? So to train an actual decision tree, what we want to do is program the logic for performing a single split. And then when we want to split the two child nodes, we can just call that same function again. So let's call it decision tree. It takes x and y as training data, and we need to give it a max depth, let's say 3 by default. So if the depth is 0, if we're out of depth, then we need to return a leaf node. And what we're going to do is just return the most common class for the points that are at that node. So if you had 6 greens and 3 blues, you'd want to say green. Otherwise, we're going to get to make a feature split. And it might be wiser here to be a little more circumspect about our splits, but let's just do it in a basic way where we only stop if we really have to. So we have a function to split the data. And then what we can do is pull out all the indices to the left and to the right in order to distribute them to the two child nodes. So the indices corresponding to the points that should go to the left are the ones for which the values of x in that column are less than the threshold. And this is a pointwise comparison of this real number threshold to this array. So we'll use a dot. And then the value that we should return in this case is a decision node. And recall it takes 4 fields, a feature index, threshold, and then the two child nodes. And to build the child nodes, this is really the key point. We're going to call this same function that we're currently defining. Because after all, what we want to do with that new node is the exact same thing we just did. If we need to stop, we put a leaf node and stop. And if we can keep going, then we make a split based on the data that are coming in. So the change we need to make is instead of using x and y, we need to use x subsetted on the points that actually went to the left. Unfortunately, though, if we do it like this, it's going to split for a very long time. It won't respect this depth. What we need to do is knock the depth down by 1 every time we call this decision node constructor. So we'll do that for both. Lastly, if we want to make an actual prediction, once again, we don't need any global description of the tree. We can just follow the local rules. So for example, if we're at a decision node and we want to make a prediction, we just need to check, is the corresponding entry less than the threshold? If so, then we defer the prediction to the left child. So again here, we're calling a function that we're currently defining. If we call this on the top level node, it will call the two children nodes. And in turn, it'll call this function again on their children nodes, eventually terminating in a leaf node, and we'll have to have a separate definition for that. In Julia, we can do that by defining another method and putting a different type annotation on the argument. So we can say predict for a leaf node, just the mode value that we assigned to that leaf node. So finally, we can generate some data. So here we make a 100 by 2 array, and then another 100 by 2 array, all populated with independent standard normals. And then we broadcast that with a sum of a row vector with two 2's in it. So this is going to shift all these points to the right 2 and up 2. And we're running into problems because there's an issue with splitting a node where the training observations are already pure. They're already the same classification. So we put this extra condition to return a leaf node that says that if y actually only contains one thing, then go ahead and make a leaf node. So we get this sort of decision boundary for this Gaussian case. And notice here, a support vector machine would do a much nicer job because the base classifier puts its decision boundary along this diagonal line. And the decision tree can't do that very well. It ends up making this zigzag line. Also because of the depth that we used of 4, in some places it ends up making these long, thin cuts because it ends up getting to try to isolate a single blue point. That's where it would be helpful to have a little more sophisticated monitoring on the splits so that we leave it as a leaf node rather than making this extra cut that puts this blue slice down here. So in summary, a decision tree is just a flowchart that makes binary decisions on one feature at a time, checking whether that feature is above a given threshold or below a given threshold. To train a decision tree, we decide how to make the split at each node greedily by just minimizing the weighted average of the Gini impurity of the training points that go to the two child nodes, where the weights are the proportion of points that go to each node. Nodes which make a split and defer the classification to two child nodes are called decision nodes, and nodes at the ends of the flowchart are called leaves. The depth of a tree is the length of the longest path, starting at the root node. Lastly, we can implement a decision tree in code by building types for the decision nodes and the leaves, and just keeping track of the local information about the child nodes. We can use that recursive approach both to train the tree and to make a prediction.